In this lecture, we're going to look in detail at the main sequence, the diagonal band along the Hertzsprung-Russell diagram that contains 85% of nearby stars. The main sequence is going to turn out to be one of the most important phases in the star's lifetime. The main sequence stars populate the diagonal band on the Hertzsprung-Russell diagram, from the hot blue main sequence stars at the high luminosity end to the cool red dwarf stars at the low luminosity end of the Hertzsprung-Russell diagram. The range of properties of main sequence stars, to remind you, is nearly a factor of 10 billion in solar luminosity, from about 1/10,000th of the luminosity of the Sun to as much as 1,000,000 times the luminosity of the Sun in the extremely rare high-mass stars. The temperatures along the sequence run from 3,000 degrees Kelvin at the red end to more than 50,000 degrees Kelvin at the blue end. Stellar radii range over a factor of 100, from 10th to approximately 10 times the radius of the Sun. And as we're going to see through this lecture, the masses of stars along the main sequence run from a minimum of 8% the mass of the Sun to more than 100 times the mass of the Sun. The upper mass limit is not well defined. Main sequence stars, as we've also seen, show a very strong mass-luminosity relationship, in the sense that the luminosity of a main sequence star scales like its mass to the fourth power. Though there are slight deviations for very low-mass stars below about 0.4 times the mass of the Sun, in general this relationship holds well over the entire range of stellar masses that we've observed. Note, however, that this is not true for giants, supergiants, or white dwarfs. The mass-luminosity relationship only holds for main sequence stars. This is telling us, first and foremost, that the main sequence is a mass sequence. Running from the red dwarfs to the blue dwarfs at the other end of the main sequence is a sequence going from low mass to high mass in order. Where you are on the main sequence is determined entirely by your mass. At the high mass end, we have the high luminosity hot blue stars. At the low mass end, we have the low luminosity cool red dwarf stars, and everything in between. Where you are along the main sequence is determined entirely by your mass. Main sequence stars are main sequence stars because of their energy source. Main sequence stars are those stars that fuse hydrogen to helium in their cores and are in both hydrostatic and thermal equilibrium. You'll remember that hydrostatic equilibrium is when pressure and gravity within the star are in approximate balance. Thermal equilibrium is when the energy generated and the luminosity, the amount of energy being lost to shining, are also in balance. It's the state of hydrostatic and thermal equilibrium that defines the state of a star when it's residing on the main sequence. A third definition for a main sequence star is fusion of hydrogen into helium in the core. This is important. Not fusion anywhere, but in the core. This fusion supplies all of the energy needed for the star via either the pp chain or the CNO cycle, or both in a transition between low and high mass stars. If we relax any of these conditions, hydrostatic equilibrium, thermal equilibrium, or core hydrogen fusion, the star must leave the main sequence. Its properties of the interior will change, and those interior changes will have exterior consequences that will change the luminosity and surface temperature of the star sufficiently to cause it to move off of the main sequence and elsewhere into the Hertzsprung-Russell diagram. Indeed, it is changes in either of these three states, hydrostatic equilibrium, thermal equilibrium, or core hydrogen fusion, that is a way we piece together the story of stellar evolution. The internal structure of a main sequence star is determined by its core temperature, its core pressure, and its core composition, the mixture of hydrogen, helium, and other heavy elements. The nuclear fusion rate, as we've already seen in a previous lecture, is very, very sensitive to temperature. To remind you, the proton-proton chain has a fusion rate that is proportional to temperature to the fourth power, and the CNO cycle has a fusion rate that is proportional to temperature to the 18th power. CNO cycle is profoundly sensitive to small changes in temperature, but both work in the same way. Higher temperatures in the core lead to more fusion energy being generated. The second piece of physics that's important to us is the relationship between gas pressure, density, and temperature through what we call the equation of state in the form of the perfect gas law. The pressure is equal to the number density of gas particles, the number of particles, atoms or molecules per cubic centimeter, a constant, the Boltzmann constant, and the temperature. It's this ideal gas law combined with gravity that sets up the state of hydrostatic equilibrium. However, we've always been paying attention to the relationship between pressure and temperature, but there's a second piece that's very important. That's the number density of gas particles. As fusion occurs inside the core of a star, we're changing the core's composition. We're taking 4 hydrogen atoms and we're turning it into 1 helium atom. That means that the number of gas particles per volume inside the core of a star fusing hydrogen to helium is slowly changing in time as more of the hydrogen, is converted into helium. We end up with going from 4 particles to 1. Notice that the density here is not the mass density, but the number density of particles, how many particles per cubic centimeter, not their individual masses. So while the mass is only changing a tiny amount with fusion, remember it's 0.7% of the mass is converted into energy when I convert hydrogen to helium, but we're also reducing the number of particles per cubic centimeter. This has a consequence for the evolution of the star. What this means is that as main sequence stars consume more of their hydrogen and convert it into helium inside their cores, main sequence stars slowly get brighter and slowly grow in radius as they age. As hydrogen is fused into helium, the core has fewer but heavier nuclei present. To maintain the pressure in the core has to get a little bit hotter. If I make N go down in P equals NKT, I have to make T go up in proportion in order to maintain the pressure balance. Higher core temperatures run the hydrogen fusion at a slightly higher luminosity. It makes a little bit more energy than the star used to need. This makes the star expand a little tiny bit in response as it rearranges its internal structure in response to the slow change in composition down inside the core. The effect is actually quite small. It amounts to less than 1% change in all of these quantities per 100 million years of life. This graph I show over on the right-hand side of the screen is based on the current state-of-the-art solar model. This is a detailed model of the interior structure of the sun, including the nuclear fusion and the slow change in composition from the sun's birth up to the present day, and indeed can project far into the future. We're going to be making a lot of reference to this particular picture as an example of how stars change their internal structure and their appearances through the course as their life begins to play out, through the course of what we call stellar evolution. This particular model is by Bacall, Pinsonneau, and Bapu, and I'll remind you all that Mark Pinsonneau is a professor at The Ohio State University. This is the current state-of-the-art solar model. In the top panel, we see the core's composition as a function of the age of the sun measured in billions of years. And we're showing 7 billion years of the sun's evolution with the dashed line marking where the sun is today. When the sun was born, it was born with approximately 70% hydrogen and about 25% helium, with a little tiny mix of metals making up the difference. So we go from about 72% to 25% and about 3% of carbon, nitrogen, oxygen, and all the other stuff. This is where we start. But as the sun ignites hydrogen fusion in its core, the hydrogen in the very central core, that central 10% of the mass of the sun, begins to go down because I'm consuming hydrogen, releasing energy, and making helium. So as hydrogen goes down, helium will rise in proportion. They crossed over 50-50 composition when the sun was about 3 billion years old. Today, when the sun is about 4.6 billion years old, the proportions have not quite reversed. The composition of the sun is now only about 35% helium. 35% hydrogen, but now it's as much as 65%, give or take, of helium. So now, while on the surface of the sun, the proportions of hydrogen and helium are the same that it started out with. The surface composition is not affected by fusion to a first approximation, but the core composition has changed dramatically. The core of the Sun is now predominantly helium, about 65%, and about 35% hydrogen. Because of that steady change in the number density of particles due to the change in composition, since the Sun began to fuse hydrogen to helium and landed on the main sequence, the Sun's radius has been slowly growing, shown by the green curve here, where the Sun's radius is now here at what we would call one present-day solar radius, but it started out at about 0.87 of its 87% of its current radius. Where today the luminosity of the Sun is here at 1 solar luminosity, when it started out it was approximately 70% of its current luminosity. This trend is going to continue so long as it continues to fuse hydrogen to helium in its core, and indeed in the future, when the Sun is about 6 billion years old, the Sun's luminosity is going to be almost 1.15, 15% brighter than it is today, and at that same 6 billion years, it's going to be maybe about 5% larger. So this change in the size of the Sun is a very, very small, slow-rolling function. The luminosity gets brighter by about 1% per year, and the radius gets bigger about half that, about 0.5% per 100 million years. Let's look at the interiors of other stars and see how they put themselves together based on their mass. Red dwarf stars are the lowest mass main sequence stars. These are stars whose masses are less than about 40% the mass of the Sun, 0.4 m-Sun. These stars are fully convective. The mass range for red dwarfs runs between about 8% the mass of the Sun to 40% the mass of the Sun, and all of them have core temperatures that are less than about 11 million degrees Kelvin. At 11 million degrees Kelvin, it's too cool for the CNO cycle to occur, so proton-proton chain fusion is the only source of energy available to the star in the core. Both the core and the envelope will turn out to be convective. These are somewhat cooler stars. Cooler gas has a different opacity to photons, to light, and as a consequence, photons cannot as easily stream out and random walk their way out to the surface as they can in a Sun-like star. What happens in that case is the bottom gets very hot, the bottom of the gas gets very hot, and you set up this slow rolling, boiling motion throughout the star. The central core, where fusion is occurring, turns out to be convective, and so the core gets very, very evenly mixed as hydrogen is depleted and turned into helium, and the outer envelope is fully convective. These are cool, highly convective stars. It's a very different structure than we see in the Sun. Lower main sequence stars have radiative cores and convective envelopes. These are stars with a range between 0.4 times the mass of the Sun, the upper limit for red dwarfs, and about 1.2 times the mass of the Sun. So in this range from 40% to 40% the size of the Sun to 20% larger than the size of the Sun are what we're going to define as this lower main sequence. The core temperature inside of these stars is less than about 17 million degrees Kelvin. For the most part, through these stars, the proton-proton fusion chain is going to be the dominant source of energy generation. However, as you go up in mass along the lower main sequence, as you go from 40% the mass of the Sun to 1.2 times the mass of the Sun, the temperature in the core is going to get larger, and the CNO cycle is going to click on and start becoming more and more important. As it becomes more important, the inner envelope is going to become increasingly radiative, and the convective outer envelope is going to start steadily shrinking. We're going to see a steady change as we go from the low mass end of the lower main sequence to the high mass end at 1.2 solar masses, a slow change in the interplay between the radiative core and this convective envelope. At the very bottom of the lower main sequence, we have a radiative core, and then immediately outside in the envelope, the core is fully convective. But that's at about 0.4 times the mass of the Sun. If we looked at, for example, the Sun today, which is a 1 solar mass star, where the composition in the core is shown about 35% hydrogen and about 65% helium, we find that we have an inner radiative core. This is the inner 1/4 of the radius of the Sun, containing about 10% of its mass. or half of the solar mass, excuse me. This is the zone of fusion. It's running on fusion at about 98% of the proton-proton chain and a little under 2% of the CNO cycle. Immediately outside of this core is the radiative zone, which extends from 1/4 of the radius of the Sun out to 70% the radius of the Sun. But at 70% the radius of the Sun, the envelope has gotten cool enough, the gas has become more opaque, and we switch over into convective transport to make that last 0.3 radii of the Sun from 0.7 to the surface is now going to transport energy being generated in the center primarily through convection. As the Sun ages, this mix of the size of the radiative and convective zone is going to change over time. It's fairly more complicated than we're going to go into in this class, but understand that whenever I show a picture like this of the state of the Sun, the operative word is the state of the Sun, the configuration of the Sun today. It was not like this in the past, it was a little different, and it will be not like this in the future. Part of that is going to be telling the story of how the Sun ages. Finally, the highest mass stars, what we will call the upper main sequence, are going to be all those stars whose masses are greater than 1.2 times the mass of the Sun. These are going to have almost the opposite structure of the lower main sequence. Where the lower main sequence had radiative cores and convective envelopes, upper main sequence stars have convective cores and radiative envelopes. These are stars whose masses exceed 1.2 times the mass of the Sun and whose core temperatures exceed 17 million degrees Kelvin. 17 million degrees Kelvin is the key. What marks the dividing line between the lower and upper main sequence is the point at which the CNO cycle fusion chain dominates core energy generation. In the lower main sequence, it's predominantly proton-proton chain. In the upper main sequence, it's essentially CNO cycle. Because the CNO cycle is extremely sensitive to temperature, it goes like temperature to the 18th power, the hot core is extremely convective. It's basically unstable to convection and is boiling and roiling away. It generates so much energy pumped into the envelope that the envelope is less dense, a bit more extended, and so becomes radiative. Radiation or photon transport is the dominant way to get energy from the fusion in the convective core out to the surface. This is, again, exactly the opposite of what we see in the lower main sequence. And so we've seen that the internal structure of a star on the main sequence is determined primarily by its mass. Its mass determines how hot the core is. How hot the core is tells you what fusion cycle, proton-proton or CNO, is going to be dominant. With the exception of the red dwarfs, where an additional factor comes into play, at very low masses, the somewhat cooler gas throughout the volume of the star makes it easier for convection to occur than radiation. Once we get to the lower main sequence, it's this combination of, am I getting my energy from proton-proton? We have a radiative core and a convective envelope. And the upper main sequence, for 1.2 solar masses and above, CNO cycle dominates. The extreme temperature sensitivity of CNO cycle makes the core convective, the envelope is puffier, and we get radiation photon transport being the most efficient way to transport energy from the center to the edge. This is the first part of this lecture has been concerned with the structure of stars on the main sequence. A question we want to ask and answer in the second part is, how long can this main sequence phase last?